slides are visible. Students.
Audible, sir. Good afternoon, sir.
Yeah. Okay. So in the last class, we were discussing about the bridges, learning bridge, and its looping problem and possible solutions. So two possible solutions we have discussed. So one is the source routing, and the second one is the spanning tree algorithm. Right, in the source routing, the packet itself or the frame itself will be having the where and all the LAN or the bridges the frame has to visit in order to reach the destination, right? And in the spanning tree algorithm, so we followed the four steps, right? The very first one, we selected the root bridge. Then the second step was to select the root ports of the bridges except the root bridge. Correct. Then later the third step was to select the the root bridge, right? Yeah, designated bridge and the root port. Then the selected root port and the designated bridge, so we made them to forward, right? And the rest of them are in the blocked states, right? So in this way we got the spanning tree without any loops. Then later I have just introduced the data link layer. So in the data link layer, there are two main sublayers in it. So the very first one is the logical link control. So it deals only with respect to the error control, right? Detection, correction, right? And controlling. So the medium access control, it deals with respect to the channel, right? And the rate at which the sender has to send and the rate at which the receiver need to be received from the sender. So these functions will be done in the medium access control. So today we will just see the complete the logical link control sublayers, in that only specific to the errors. Right. So as we are saying logical link control, so it's a second bottommost layer, and in the logical link control or in the data link layer, so the data will be in the form of the bits, correct? So bits, and all the bits will be put it into a one particular format, and that format we call the frames, correct? The frame, right? And there is a point to point communication in the logical link controller. So a device A will be there and device B will be there. So there is a point to point communication, so there is a exchange of the formulated frames between the A and B, right? And we have seen that, so during this transmission, there will be the addition of some kind of a interference, kind of like the crosstalk. Sometime we will, get during the conversation with your friend or your family, right? And also the noise, right? So there will be addition of the noise into the link, right? So as a result, we won't get the signal as the signal it was sent by the A, right? So we won't get the original signals, right? So this addition of the noise or addition of the interference to the original signals, right? So these we call the errors, right? And some of the applications are tolerable with certain extent of the errors, and some of them cannot tolerate. For example, the audio video applications, right? So certain level of errors they can accept, right? Maybe two or three errors they can acceptable range, but the errors are like 10 errors, right? 15 errors. So like this also, the audio video applications are not acceptable, right? and even there is a change in only one bit errors, right? So it is difficult to understand what they have sent the data. So those we call the text data. So this text data, we need the very high level of accuracy, right? So now we will see the what kind of errors exist during the transmission of frames from one node to the another node, or one device to the another device, right? So in the logical link control, so there are two types of errors. So very first one is the single bit error, and the second one is the burst error. So as the name itself, it gives the definition of the single bit error, right? So single means only one bit of error exists in the data. For example, so changing from the 0 to 1 bits, so these are bits, or 1 to 0. So either this one will exist or this will exist, right? So this kind of errors we call the single bit error. And in the burst error, there are more than two bits are changed from 0 to 1, right? For example, we are having the bits like 0 1 0 1, right? So in the single bit, what happens? Suppose the error is there, then we will get like this, right? So there is error in the first bit, correct? But in the burst error, what will happen? So suppose this is the actual data we are sending, right? In the burst error, if it exists, then it will be like this, right? So there is change of the first bit and the change of the third bit, right? 0 to 1, 0 to 1, or we can change to 1 to 0 as well. So if you do this one, 1 to 0, also this is the burst errors, right? So now we'll see the little more bit about the single bit error. So as I said, there will be only one bit of a given data unit is changed. So here you can see, so this is the actual data, AD, actual data, and it contains the 00000010, right? So there are total 8 bits will be there, right? And so whenever we transmit this data through a link, right? So through a link, so either the wireless link or wired link, right? So I'll better, this is the wireless dotted one, and the continuous is the wired, right? So suppose these any kind of things, if you take the transmission mode, wireless or wired, there might be change of the bits due to the noise or due to the interference like the crosstalk, right? So here the, so this is the source and this is the destination. The source has sent this data, so when it reaches, so we are getting the four zeros, right? Then 1010, but here what we have sent is 5010, right? So there is a change of bits. So this is the bit which has changed from the 0 to 1. So 0 to 1, the bit has changed, right? So this one we call the corrupted single bit error, right? So in this the single bit error, it doesn't appear more likely in serial transmissions, right? For example, serial data transmission. Suppose the sender sends the data at the frames. So I don't want to say the data as we are in the data link layer. I'll say it's a frame. So sender sends the frame at a rate 1 Mbps, right? And this means that the bit lasts only for 1 microseconds, right? So time is like 1 divided by 1 Mbps, correct? So it will be like 1 microseconds, right? So this error will exist only for the 1 microseconds, right? For a single bit error to occur, right? And the noise must have duration of 1 microseconds, right? But this kind of existing the noise which has the duration 1 microsecond is very rare. We cannot get, very rare. and normally the noise lasts much longer than this, right? So the single bit error will occur very rare, right? So it's a very negligible, so we can ignore this kind of errors, right? So the single bit error mainly occurs in the parallel data transmissions, right? For example, if 8 wires are used to send the 8 bits of a byte, right? If one of the wire is noisy, then signal bit is corrupted per byte, right? Suppose like this parallel transmission is there, right? So there are 8 lines are there, and you are sending some data here, something like this. So these are parallel transmissions. Suppose one, so whatever the here whatever we are receiving, suppose this is the error. Instead of 1, I have received the 0, and this is a 0 1 0 1, right? So this wire is a single bit error, and this is a corrupted, right? So it's highly used in the parallel data transmissions, and we can easily identify the errors in the parallel data transmissions, right? So the second one is the burst error, right? As I mentioned in the earlier slide, there are more than two bits are changed from 0 to 1, or from the 1 to 0, right? 0 to 1, or from the 1 to 0. So this kind of errors we call as the burst errors, right? So for example, you can see here in this diagram, so this is a complete frame, right? This is the complete one frame, and the source is sending. So this is the frame, and this frame is sent by the source, right? And this is the guy who is receiving, and this is the frame it has received, or you can say right here. So I'm very bad uh, writing in the slides. So here you can easily see that. So the data which the sender has sent, and the data or the frame which is received by the receiver, right? Both are changed. So there is a change in the bits from the 0 to 1, and 0 to 1 here, and 0 to 1 here, right? So multiple bits have been changed from 0 to 1, or 1 to 0, right? So this kind of errors, or this kind of error in real time, we call the burst error, right? So here the duration of noise in this burst error will be more than the duration of noise in the signal single bit error, right? Because of more than one, or the more than two bits will be changed from the 0 to 1, or 1 to 0, right? And this kind of errors will occur during serial data transmissions, right? And the number of affected bits depends upon the duration of the noise, and the data at which the sender is sending, and the data at which the receiver is receiving. So that's the data rate, right? So this is about the errors. Now we will see the error detecting techniques, right? So there are four different types of errors detecting techniques. The very first one is the single parity check, and the second one is the two-dimensional parity check. Then third one is the checksum, and fourth one is the cyclic redundancy check, right? And in today's class we'll see the single parity check. So how to detect the errors using the single parity check, and how to detect the errors using the 2D parity check and checksum, right? So the single parity checking is the simple mechanism and inexpensive to detect the errors, right? So in this single parity check technique, a redundant bit is also known as the parity bit, which is appended at the end of the data, right? So whatever the frames we are sending, right? This is the frame, and we are having here the bits, right? Either 0, 1, 1, 0, 0, 1, correct? So this is the frame, and the sender is sending this frame to the receiver, correct? So along with this, we will be adding the one more field called the parity bit, right? We are adding a parity bit, either 0 or 1, right? So depending upon what kind of parity bit you are, so what type of single parity check it is, either it is a even parity check or it's a odd parity check, right? So we'll see that. So this is for the even parity check, right? So the sender is sending the data or the bits. So this is a frame, correct? So in the frame we are having the bits 10110111, correct? So here we need to compute the parity bit with the help of this data, right? Suppose as we are sending, this is the even parity check, right? So this is the even parity check. I have not written. So you can see here even is there. So that's why this is the even parity check. So how to use the even parity check? So in this data, so ones are 5 and zeros are 2, right? So in the even parity check, single parity check, if the ones, right? Ones, 5 times 1. So we are having 5 times 1 bit, right? Or just say the ones, and 2 times, right? Zeros. So this is ones and this is zeros. So as we are saying even, so wherever the ones are there, right? 5 ones are there and 5 ones are odd, right? So in order to make a even, right, we need to add a one more 1, right? So that's why here I have written the 1, right? For the even parity check, if the ones are odd, right? Odd. So ones here are 5 times. So 5 is a odd. So whenever it is odd, we need to make it even. So in order to make it even, we need to add a 1. So this 1 is the parity bit, right? Suppose, so we are having the like this 1 0 1 0 1. So 1 0 1 1 1 0 1 0 0 1, right? So suppose like this we are having the data, right? So this is the data. So for the even parity bit, what happens? So how many ones are even? So how many ones are there? One, this is the one, this is the two, this is three, and this is the four. And so total numbers are four, and four is a even. So that's why we have to add here zero, right? Guys, have you understood or not? Students?
Yes, sir.
Yes.
Okay, fine. So
Yes, sir.
this frame now we need to transmit to the receiver through the transmission medium. So whatever the data it was there, right? And here we need to compute the parity bit, right? So for the computing the parity bit, how we do? Again, we need to check whether it is even or odd. So this is 1, 2, 3, 4, 5, and 6, right? So it's a even. So if it is even, then accept the data. If it is not a even, then reject the data. Right? So this is for the even. Suppose it is a odd, right? Suppose I'm doing the odd. So if it is odd here, it's not even now. So it's a odd, right? So if it is a odd, wait. I'll just remove this so that I can discard. Yeah, now. So now I'll say it's a odd parity check. So ODD, correct? And sender is sending this data, right? So the odd parity check, how it works. So wherever, so here only we'll check. So how many ones are there? 1, 2, 3, 4, 5. So 5 is the odd, right? So whenever it is a odd, then we no need to make it again. Like we if you add 1, it will become the even, right? So I want the odd parity check. So in this case, so here it will be the 0. Why 0? Because already the number of ones are odd. So the parity bit here is the 0, right? And the same, this frame will be sent to the sender through the transmission media, and here again the computation of the parity bit will be taking place. So this will be the 0 now, right? So now it will check the parity bit. So again here 1, 2, 3, 4 and 5. 5 is a odd, right? So if it is odd, then accept it. So if it is a n, then reject the data. So this is how the odd parity check, single parity check will be working here. So what are the drawbacks in the single parity checks? So it can only detect single bit errors, which are very rare, right? So 0, 1, 0, 1, 0, 1, right? So this is the, suppose I'm using the even parity bit, right? So even I'm doing. So for the even, this is the frame, correct? And the parity bit. So as we are saying even, so it should be the 1 here, right? Because odd number of ones are there. 1, 2, 3. 3 is odd. So that's why I'm writing 1. So if I add 1, so it will become the even, right? Suppose this we are sending the data to the receiver. So this is sender and this is the receiver destination, right? And here I am receiving the data like 1, 1, 0, 0. So 2, 4, 6, 2, 4, 0, 0. So this one, this 0, right? And I'll write 1 and this 0, this 0, right? No, no, wait. So here G, so sorry, 0, 1, 0, 1. This is the data we are sending to the sender, and this is the, so suppose I'll put one more 1 here, and as it is a even, so the parity check will be the 1 here, correct? This is the sender, and in the destination I want to change 2 bits, because here we are saying that it can only detect single bit errors, right? So instead of 0, I will write 1, and I'll keep the 1 as it is 1, and I'll write the 0. 0 I'll change to 1, and it is 1, and it is a 1, right? So it's a odd, correct? So odd parity bit is 1, correct? Because it's a even, right? So here it cannot detect the errors, right? So how to detect the errors? If it is a 0, then it can say this discard. But it says that the parity bit which is computed at the receiver side, it's a 1. So it's correct only, right? So that's why we cannot use the single parity check whenever we have, or whenever we detect more than one errors, right? And if 2 bits are interchanged, then it cannot detect the errors as well, right? So here we have changed this bit, and this bit. Then also we cannot check, because in both the way we are both side we are having the same parity bit. So here with the diagram I have shown, so there is a change in the bits, right? So then also we cannot check it. So the second one is the two-dimensional parity check, right? So in the first parity check, we are not able to detect more than two errors which is exist in the frame, right? So in order to provide the solutions, we'll go to the another technique called the two-dimensional parity checks, right? So it will be like it will organize us in the form of the table, right? Whatever the data we will be giving, so it will organize in the table, and it will compute the parity checks in each row, right? In each row as well as in each column, right? I'll show the uh, example, so you'll get a complete idea instead of going through the complete this thing. So this is the original data, right? So double one double zero double one one zero and one zero triple one zero one zero, right? Now I will organize this data, right, in terms of the table, right? So we have made, this is the complete data, and we have made a four section or four segments, right? You just say the section. So this is section 1, section 2, section 3 and section 4, right? And we have put it in this order, in the same order. So double one double zero triple one zero, so one zero, right? Triple one zero one zero, so one zero triple one zero, right? And these two remaining as it is, right? Now, so whatever we have done for the single parity check, for the only one error checking, so we will be doing like this. So first we will be calculating the column parities. So here, right? So this is for the even parity check. So you check this column. So this is the column 1, right? Check. So how many ones are there? Two ones are there. So the parity check for the even is the 0, correct? So the column 2, right? So how many ones are there? Three ones are there. So one, two, three, and it's a odd, but I want a even, so I need to add one here, so it's a one, right? And the column number 3, right? So we are having how many ones? Two ones, that's why it's a 0, right? Already it is even. So column number 4, we are having three ones, so it's a odd, so we, in order to make a even, we need to add one, right? And so on. Now we got the column parities. Now we have to get the row parities, right? So in this row, right? So how many ones are there? One, two, three, four, five. So five is an odd, we need to add one in order to make a even, right? So similarly here you can see, so how many ones are there? One, two, three, four. So four is a even, right? So no need to add a one, that's why we are adding the 0, right? So we got like this. So the same thing we will be computing at the destination side, right? This is done at the receiver sender side, and we will be checking at the destination side. So if both row parities and the column parities matches, right, then only the, if it is even, then only we will accept the data, otherwise we won't accept the data, right? So what are the drawbacks of the 2D parity check? If two bits in one data unit are corrupted and two bits exactly the same position in another data units are also corrupted, then two, yeah, exactly. So you can check this here only. So instead of one here, you can make a 0, right? Instead of 0 here, you can make a 1, right? And instead of 0 here, right, you can make a 1, and instead of 0 here, you can make 1, right? We'll get a different, we'll get the column parity is different and the row parities will be the different, right? So this is how we can detect, and this technique cannot be used to detect the 4-bit errors or more in some cases. So again it is ruled out, right? So single parity check, we cannot use it for more than one, and two-dimensional parity check, we cannot use it more than for the more than 4-bit errors, we cannot do it, right? So we have one more technique, that is the checksum, right? Checksum. So it's an error detection technique based on the concept of the redundancy, right? I'll give the example so you'll get a clear idea. So whenever the data is transmitted, so as I have discussed earlier, so there will be signal noise, and sometimes the synchronization error will be there. So as a result, either data will be lost or data will be corrupted, right? So it's very really very important to have a way of verifying the data that has received the data received the data by the receiver, which was actually sent by the sender, right? And checksum requires a less transparency and will provide for ample error reductions, right? More than 4 error deduction also it is possible, right? So checksum cannot detect compensating errors. One bit goes from 0 to 1 and 1 to 0. Just we'll see with the example. So yeah, so here in the checksum we are having the two entities. One is the sender and another one is the receiver, right? So a checksum is generated at the sending side, and this checksum generator means sender, which subdivides the data into equal segments of n bits each. So we are having the like this frames, and this bit frames will be divided into number of equal segments, right? Suppose 4, and these are having the number of bits in this segment, and this segment and this as well, this are having the equal bits, and all these segments are added together by using one's complement arithmetic, right? I think you might be knowing the what this one's complement arithmetic, right? So we need to add two numbers or two bits, two data bits, right? And if there is any carry is there, then again we need to add that one at the uh, MSB, right? Then we need to take the inverse or the complement of the whatever the result that is there. So whatever the result we get, that is the one's complement arithmetic. So the sum is completed, complemented and appended to the original data. So that's what they call the checksum field. So the extended data is transmitted across the network. Let's see the example, right? So the data bits are there. So these many data are there, and we are dividing each into section, or you can say this segment also. So as we are using segment in the transport layer, so we don't want to use that again here in the data link layer. So we have written the section 1, section 2, and so on. So all the same bits will be there, right? And we will be adding all, so till, so this one you ignore, I don't know why they have written, so this is not necessary, right? So all the sections we need to add it. So whatever the carries will be there, so that carry we need to take it to the um, MSB, and we need to add it, right? And whatever the sum we'll get, right? So that sum we need to complement it, right? And this complemented data we call the checksum, right? So what that checksum we need to do is, whatever the data, actual data is there, along with the actual data we need to append this checksum, right? This is the frame. Again there is a mistake here, and through the transmission medium we have to send the data to the center, right? In the sender, what it does, the same whatever the work they have done, the same kind of work we have to do, whatever the data we have received. So this is the frame, right? So this frame we have received, right? So this frame again we need to complete frame, we need to divide it into the certain number of sections, and each section should have the equal number of bits, right? And we need to sum it, and after summing we need to complement it, and whatever the result we get, so this result right? Result should be all zeros. And if it is 0, then only it will say that there will be no errors in the data, right? So we'll see this data, right? So I'll just do it the other tool so that you will follow easily. It takes time. So here we are having the this data 10001 10001. So this is the 1 and 0 1 2 3 4, right? 8 bits are there. So 2 4 5 6 7 8, 2 3 4 5 6 7 8. One is missing. So anyway, and let it open, so we'll go do it, right? So now we will do the checksum so that you will understand more clearly. So the actual data, right? So 1001 1001 and 1110 0010 and 0010 0100 and 100 0100, right? So like this is the data. I'll just make it bold and increase the font size. Yes, so this is the actual data. And here, so how many bits are there? 32 bits are there. So 32 equally we need to divide. So equally, if you divide it, it will be 8 bits with a 4, right? So k equal to 4 segments, right? And each segment should consist of 8 bits, 8 bits for the each, right? So let's do it at the center side, right? So now we need to take the starting two segments, right? So first 00100110001, right? Then the second segment is 1110 1110 0010, right? So this is the one. So now we need to do the first ones complement arithmetic, right? So ones complement arithmetic will be like we need to add these two. So 1 0 will be the 1, right? And 0 1 will be the 1, right? Yeah. And 0 0 will be the 0, and 1 0 will be the 1, right? So 4 bit is done. So I'm giving unnecessarily this. Yeah, correct. Yeah, correct. So 1 0, again it will be the 1, right? And 0 1 will be again 1, and 0 1 will be again 1, right? And here important one is, so 1 1, it will be like 0, and there is a 1 carry. So here it will be the 1 carry, right? So 1 carry will be there here, and this carry we need to add it back here. We need to add, right? So that, okay, we need to add here this one. Now what we'll get, so 1 1, it will be 0, and so 1 carry here, and again 1 1 will be the 0 and 1 carry here again, and 0 1, 0 1 will be the 1, and this is again the no carry, so as it is the 1, so remaining will be the same 1 1 1 and 0. Right, so we got 0, 5 ones and double 0. Guys, are you following or not, students?
Yes, sir.
Okay, now so yeah, so this is the second bit we have added here, right? And this was the first one, correct? Now we have to add the this bit, so let's go through that. So we are having double 0 1 0, right? 0 1 double 0. Good. So again we need to do the summing of this. So 0 0 plus 0 0, and 0 plus 0 0. So 1 plus 1, it's a 0, and carry 1. Okay. So 1 will be the carry. Good. And again 1 plus 0 1, and again 1 plus 1, it's a 0, right? So again we'll be having one carry here. Okay. So again here we are having 1 0, right? 1 0 1, and that is again the 1. So again it's a 0, and carries 1 again here, correct? So in this one here, good. So here 3 ones are there, so 1 1, so it's a 0 1, so 1 is the carry, correct? And already we are having one carry, so again 1 1, it's a 0, right? 0 and 1, it's a 1, yeah, it's a 1. Then so here, so 1 1 1 0 1 and 0 1, so it's a 0 here, and 1 is the carry. So 0 0 0 0 plus 1, and it's a 1. So we got 1 0 1 0 and 4 zeros, right? So we don't have any carries, so we no need to add again. So now we are left over with the last, right? So this one, so I'll add here. It's a 1 0 0, then 0 1 0 0, right? I'll add this. So if I add here, so what I will get is, so double 0 1 0 and 0 1 double 0, and we'll get one carry here, right? So here I'll get one carry, and this carry I need to add it back. Yeah. So if we add that, it will be like 1 here, then make this, then finally what we will get is double 0 1 double 0 1 0 1. So this is what we will get, this is the sum. Then we need to take complement of this, So complement means we need to take complement. So I'll write here, it's a sum. Need to take complement of sum. So if I take complement of sum, it will be the checksum, and that is like 1 1 0 1 1 0 1 0, right? So wherever it is 0, it's a 1. Wherever it is 1, it's a 1, a 0, right? So this is the data we are having now. Now, so this is the sender side, and we are having the receiver side here. Receiver side, and the data flow from sender to receiver will be like this. So the actual data 1001110, right? 11100010001000 and 100 and 0100. So this is the actual data. Along with this, I am adding or padding the checksum. So checksum is the double what is this, double 1 0 double 1 0 1 0. So this is the actual frame. The sender is sending this frame to the receiver here, right? So sender will be sending the same this one. So the operation whatever we have done here, the same to same operation we have to do till this point, right? So till the fourth segment, because 1 2 3 4 same to same segments are there, and same thing we need to follow, right? So I will write the final one, right? So what we got, the final one, we got this one, right? 0010. So 001001001. So that's what we got from here. This is final. So with this we are adding the this checksum at the sender, at the receiver. So that's like 110110110, right? So whatever we have done here, the same to same we have to do here also. So better in order to avoid the confusion, I'll just select it and paste it here, and I'll write here it's a receiver side, right? So whatever it was there, I'll keep them as it is, so that you'll get a clear idea. Okay, but here one addition is there. So what is that addition is? The checksum one, right? So we are having one checksum 11110111010, right? And till here it's fine. Yeah, till here it's fine, correct? So now we have to take this data as well at the receiver side, correct? I need to take it down. Good. I'll take one more, another 2 minutes. I'll just finish. So 110111010, right? Then I will sum it, right? If I sum them, so what I will get is, I'll just sum this one. So it's a 1, right? And here also 1. So 1. So 3 bits 1, and here also 1, correct? And it's 1. So total we will get 1 1 1. So all 1, right? So we don't have any overlap. We don't have the 1 1 in both the rows, right? So all 1. So this is the sum actually at the receiver side. So this is the sum. And so we need to take the complement of sum, right? So that will become the checksum. So if you take the checksum complement, we will get 0 0. So 0 0 0 0 will get. So whenever if you see at the sender the receiver side, if checksum is 0, then the data is correct. So there is no errors in the frame which are sent by the sender. Okay, so this is how we need to calculate the checksum. So is it clear, or should I give one more example? Students, is it clear? Anyway, I have given a step by step, so you can understand very easily.
Yes, sir. Clear, sir.
Yes, sir.
Okay. Okay, thank you then. So we'll start now. Yeah, this was the last slide. Yeah, we'll start now. We'll take the attendance.